Now, today's session, I think we can go for the today's session, relation functions. Some topics here, so we are not going to teach this, but we are going to share our experiences during the past so many years. In this chapter, this relation functions, maybe easy topics are so many things deeply we have to understand the definition of relations and functions, everything. And then also equivalence relations. The first concept is equivalence relations and equivalence classes. Equivalence classes that we are going to discuss now. Because we had the beginning also, we are very eager to know all about this. And then out of our experiences, you can share many points. And also, if you know that any points, you know that also we can learn from you. That's what we are sharing. We are going to share our experiences only here, and then so that we can mutually benefit from this session. That's what the idea of doing this session. So you are all very seasoned teachers, experienced teachers only. So we are not going to teach or something like that, but we are going to share our experiences. That's I think. First of all, so equivalence relations, you know that already we have taught the children equivalence relations and equivalent classes. Some and also we are going to discuss about the transitive relation. Transitive relation in some problems that students are finding a little difficult, so that we can have the clarity of knowing all these things. That's what I took the topic relation functions and equivalence relations and equivalent classes. Yeah. Let us proceed with the topic. I know that equivalence relation, you know that. I'm not going to the definition. Through an example, I'll go to the next definition, I'll go. Just as the square bracket A, if you write, that is equivalence class of the element A. Equivalence class of element A is the set of all elements X, set of all elements X, which belong to the set A, and which is related, X is related to the element A. All the elements related to A. The set of all elements which are related to A, that is a subset of the set A, the subset of set A. This subset is called equivalence class. Equivalence class containing the element A, or equivalence class of the element A. Okay. For example, define a relation R on a set Z of integers by R, the relation R is equal to set of all A comma B such that A and B are integers and A minus B is divisible by 3. The relation A minus B is divisible by 3. This is a simple relation only. So this relation is an equivalence relation. We know that, all of you. That I don't think there is a need of proof for this. This relation R is an equivalence relation because the elements taken from the integers. So A minus B is divisible by 3. A minus B is divisible by 3. It is an equivalence relation. You know that it is reflexive, symmetric, and transitive. Therefore, it is called the equivalence relation. Now we are going to see a special topic. We call it as equivalence class. So there are three subsets of integers I have written. So -6, -3, 0, 3, 6, 9. These are all multiples of 3 or divisible by 3. Or each element is divisible by 3. This is also is called an equivalence class of 0. Equivalence class of, or we can write equivalence class of 0 or equivalence class of 3 or equivalence class of 6, whatever it is, or 3 times k, where k is an integer. We can write on this one also. So we can write equivalence class of 3k or equivalence class of 0. Sorry. This subset of A is called equivalence class of 0. And then this another subset A2 is also the -5, -2. A minus B is divisible by any two elements you take. the difference is divisible by 3. A minus B is divisible by, suppose A is equal to 1 and B is equal to 4. So 1 minus 4 is divisible by 3. So each element, any two elements, if we take A comma B, so A minus B is divisible by 3. Therefore, this subset is also called the equivalence class of 1, the element 1, or equivalence class of the element 3k plus 1. Equivalence class of 1. This is a 1, or we can write 3k plus 1. Equivalence class of 3k plus 1. Okay, also we can write. So multiples of 3 plus 1. Yeah. And another subset, A3, it is minus 4, minus 1, 2, 5, 8. So the difference of any two numbers are A minus B. A and B are belongs to A3, and A minus B is divisible by 3. Of course, we know that. This is also another subset of A, subset of integers, the set A, or subset of integers. Okay, this is also an equivalence class of 2, the element 2, or we can write equivalence class of 3k plus 2, or equivalence class of 1, or 3k plus 2. K is an integer, or the equivalence class of 2. If we write the element square bracket using the square bracket, 2 means it is the equivalence class of 2. Okay, these are the 3 equivalence classes. So 3 subsets. These 3 subsets are called a partition of the set Z. Partition. Partition means what do you call the mutually disjoint. Mutually disjoint sets. Mutually disjoint sets means there is no intersection. A1 intersection A2 is an empty set, and A2 intersection A3 is also empty set, and A1 intersection A3 also empty set. This is one of the condition. So each subset is a mutually disjoint subsets, and then these 3 subsets divides Z into the 3 equivalence classes, and the union of all, the union of A1, union A2, union A3 will give the set of all integers. Set of all integers. So this equivalence relation has have 3 equivalence classes. The equivalence class containing the element 0, first one A1, and A2 is the equivalence class containing the element 1, and A3 is the equivalence class containing the element 2. Okay, or any element, you can write any element containing 6, any element. That means here 0 is related in the A1. If we take 0 is related to every element in the set A1. Each and every element 0 is related. 0 is related to 3, 0 is related to 6, 0 is related to 9, 0 is related to minus 6. Understand? So 0 is related to every element in the set A1, and because 0 minus 9 is divisible by 3, 0 minus 6 is divisible by 3. Okay, so each and every element is related to each other. Every element is related to each other, and also this is one of the equivalence class. So 3 equivalence classes. These are 3 subsets of the set of all integers. 3 subsets. If it union of all the subsets, if we take, we'll get the integers, and each subset. So intersection of AI intersection AJ means or A1 intersection A2 or A2 intersection A3, all empty sets. Okay, they are mutually disjoint sets. Yes, this is a simple example. So that's what X belongs to A. X is an element of the set integers, and X is related to A. Every element is related to the element A. That is the element 0. For example, equivalence class of 0. So instead of A here, if I write 0, so all the elements X which is related to 0 and belongs to set of integers is called the equivalence class of 0. Same like that, equivalence class of 1, equivalence class of 2, or we can say equivalence class of 2, the containing the element 4. What is the equivalence class containing the element 2? Means that is A3, the subset A3. So every subset is called equivalence class. Okay. So anything, if you want to add this, you can add anyone. You can add this here, and otherwise I'll go to next the definition of the equivalence class. So that they may ask you in 1 mark question or something like that. So this concept is a little bit given in the textbook. Anyhow, with the example it is given. So we can have so many examples here in this equivalence class, and then we can teach them effectively. The equivalence class of A is equal to set of. Yes, ma'am. Next.
In the first line, equivalence class of 3K or equivalence class of 0, and there you write some more examples, not examples, the other way, the 3K.
3K means 3 into.
That's
sorry,
what I want you to write or maybe.
Or, okay.
Or it is equivalence class of 3, or it is equivalence class of 9, or it is equivalence class of -6. They are all one and the same. That three, that I think. So
or equivalence class of 3.
Or it is minus 6. Exactly.
-6 because so all the elements which are related to -6 in this set, that forms a subset. That set is called the equivalence class of that element. That's all. That's what generally it is given here. Thank you, ma'am. Yeah, and then here equivalence of 3K plus 1. Suppose K is equal to 0. So 3K, 3 into 0 plus 1 is 1. Or you can put any integer for K. Suppose if you put K is equal to 2, 3 into 2, 6, 6 plus 1, 7. So the equivalence class of 7. We can call it as the A2 as equivalence class of 7, or equivalence class of -2, or equivalence class of -5, etc. And also A3 is a 3K plus 2. 3 into K, 0 plus 2 is 2. Or if I put 1, K is equal to 1 here. So 3 into 1 plus 2, that is a 5. So it is called equivalence class of 5. Or you can call it as equivalence class of -4, etc. Anything we can have. Yeah. So just this is a simple example we have gone through, and then I may go to the.
So in the class also they can give instead of course we teach them through the theory, and they can number the children 1, 2, 3, 40 children. You can assign number to each child, and then you say, now I want you to get into groups following this rule. Some rule you give, like A minus B is divisible by 3 or whatever it is. You give, and then ask them to divide them into get into groups. And you give one another rule where it is not equivalence relation. And they will find, children will find difficult to, some children will be common to 2 groups. So they will not be able to divide themselves into exactly groups, different disjoint groups. Then you can tell them, so this is the magic of equivalence relation. So when it is equivalence relation, you will be divided into disjoint different groups. And each group,
yes, ma'am. I would also add one point to this, ma'am.
Yes.
Number of equivalence classes will be actually the number of reminders, which when a number is divided by 3.
So
the number of reminders 0, 1, 2. That is why the class 0 is equal to class 3 because class 3 reminder we don't say. It is naturally it becomes class 0 itself. Isn't it? So if a number divisible by 5 means we can form 5 disjoint sets like this, which are each and every one is equivalence relation on its own and mutually disjoint, and union will be the whole Z itself.
Yes, welcome. Thank you, ma'am. Yes.
Some games like this in the class so that they understand. Where it is equivalence class only like cutter, it will divide them into groups, disjoint groups. If it is not equivalence relation, no, it will not divide.
Yes, ma'am. So this is that is actually what we have discussed here. If R is an equivalence relation on a set A, then R divides the set A into mutually disjoint subsets AI. AI means I is 1, 2, 3, etc. N, called partitions of A. Partitions, we know that partition. Partitions of A satisfying, that is the 3 conditions. All elements of AI are related to each other for all I, and no element of AI is related to any element of AJ where I is not equal to J. That means that is a mutually what we call pairwise disjoint. We call this disjoint sets. And the the union of all the AI, the union of all, that is equal to, that is A. That is A1 union A2 union A3 etc. AN is equal to the set A. That means if the union of all the subsets, it is a set A, the set A. And that is AI intersection AJ is an empty set. That's what mutually disjoint sets, where I is not equal to J. That's what we have discussed. These are the 3 points that satisfy. Then it is an equivalence class satisfying all the 3 points. Then we can say that A1, A2, etc. AN are called equivalence classes. Are called equivalence classes. I think anything if you want to add with this, you can, or any doubt you can have, you can discuss. Please, teachers, you can discuss anything here, or any doubt, any clarification required, you can ask. Or you can, if you know any other point extra also, you can add up here so that we can take that point. Yes. As I go to one more example. This relation is somewhat a different relation. Let the relation R defined by a set of ordered pairs, that is A comma B related to C comma D. If and only if A plus D is equal to B plus C. The sum of the extremes is equal to the sum of the betweens. We call it as like that. A plus D, the first and last, is equal to B plus C. On this set A contains only 5 elements. The set A contains only 1, 2, 3, 4, 5. The easy, simple set I have taken. So find the equivalence class of the element 1, 2. Find the equivalence class of the element 1, 2. Okay. How to make that? It is an equivalence relation. I think all the teachers, we know that it is this relation is equivalence. It is reflexive, symmetric, and transitive. Also, it is an equivalence relation. We know that already. We have taught them one thing. And now we are going to find the equivalence class of 1, 2. This element 1, 2 is related to what are all the ordered pairs belong to that A cross A. A is a set, no? So A cross A will have how many elements? There are 5 elements in A. So that A cross A will have 25 elements, 25 ordered pairs from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. So that A cross A will have 25 ordered pairs. So that from the 25 ordered pairs, we have to take the elements which are related to 1, 2. The element which are related to 1, 2. How to make this elements related to 1, 2. So here the 1, 2 is related to 1, 2 because A plus D is equal to B plus C. So A plus D is equal to B plus C. That means that is 1 plus 2 is equal to 2 plus 1. So 1, 2 itself, the element itself is related to 1, 2. Okay. And another element is that is 1, 2 is related to 2, 3. Because this is 1 plus 3, which is equal to 2 plus 2. You see that? So 1 plus 3 is 4, which is equal to 2 plus 2. So 2, 3 also related to 1, 2. Like that, this first 4 elements are related. And 1, 2 is related to, sorry. Sorry, is related to 3, 4. 1, 2 is related to 3, 4. Because this 1 plus 4 is equal to 2 plus 3. And also 1, 2 related to 4, 5. Yeah. So 1 and 5 are related, and sorry, 1 plus 5 is equal to 2 plus 4. All are equal. So I think these are the 4 elements which are related to 1, 2 from the set A cross A. We have to A from set A to set A. That is A cross A. So A cross A is an ordered pair. A cross A containing ordered pairs. Sorry.
Excuse me, sir. I have
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Sir, now by seeing the answers, we are using trial and error method to find the answers. Without trial and error method, do we have any other method to calculate it?
I don't think so. This question, I think trial and error method only we have found. If anyone knows this, any other method to find the answers, you can.
Actually, we can do slight change in that expression. We can write like a minus b equal to c minus d, so that the difference of first two elements is equal to the difference of the second element. In that way, we can modify that statement.
Okay.
And that would be easy, perhaps.
Okay, a minus.
I have the same method, sir. 1 and 2 difference is 1. So if you take in the 25 ordered pairs, consecutively difference 1 comes. That same order you have to take.
You so can please write, sir, that a minus b equal to c minus d. So the first bracket, no, the difference will be -1 actually. So wherever that -1 difference comes, all those ordered pairs we can pick from the A cross A.
Okay. That is also possible. Yeah, just that's all. That is, keep it in mind only. We are doing all this. The difference is 2, difference is 3.
Yes.
Like that only. I think these are the 25 ordered pairs I have separated into. This one equivalence 9 equivalence classes we are coming. Equivalence class containing the element 1, 3, 1, 4, or 2, 5. Like that we can have. So equivalence class containing this 1, 5. Equivalence class containing 5, 1. I think these are the 9 equivalence classes we can form from the set A cross A. I think so. So these are the equivalence classes. So the first one is the answer 1, 2. Find the equivalence class of 1, 2 means the set of all ordered pairs which are related to 1, 2 from the set A cross A. That subset we call it as equivalence class of 1, 2. And then this equivalence relation, this question is often I want to discuss, or whether you know it, or I think many of you know that. Anyhow, let A is a set 1, 2, 3. Find the number of equivalence relations on A containing the element 1, 2. Number of equivalence relations, not classes. Number of equivalence relations on A, on the set A, containing the element 1, 2. Set A means that is A cross A. We'll have A cross A. So the equivalence relations on A containing the element 1, 2. So how many equivalence relations we can form from the set A? That we have to discuss. This question is one more question. So many different way they are asking. That's why I wanted to mention this. Anyhow, clarify this. So the one equivalence relation that is set A. Set A1. So this is a very smallest equivalence relation. I will write all the equivalence relations of the set A. Finally, we can get the answer. So 1, 1, 2, 2, 3, 3. Yeah. So this is an equivalence relation containing the smallest number of elements. That is a less number of elements from the set A. So 1, 1, 2. It is reflexive, symmetric, and transitive. Yeah. Do you agree, all of you? Any difference of opinion or anything else you can discuss here? This relation is reflexive, symmetric, and transitive. Yeah. Do you agree, all of you? And
yes, sir.
A2 there's a minimum number of elements we should have from each equivalence relation. 2, 2, 3, 3. And then 1, 2. If you add 1, 2, I have to add 2, 1 also. It is also an equivalence relation. And A3 is another equivalence relation. 1, 1, 2, 2, 3, 3, 1, 3 and 3, 1 is also another equivalence relation. A4. This 1, 1, 2, 2 is compulsory mandatory because reflexive relation. 3, 3 and 2, 3. Like this. And the 3, 2. Yeah. And the last one containing all the elements. 1, 1, 2, 2, 3, 3, 4, 4. Sorry. 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, and 3, 2. Yeah. These are the 5 equivalence relations we can form from the set A. So the element containing the equivalence relation containing 1, 2 is this one, A2 and A5. Only the 2 equivalence relations containing the element 1, 2. Am I right? I think. So these are the 2 equivalence relations from the set A. Okay. I don't think any other equivalence relations are there. These are the 5 equivalence relations we can form from the set A cross A or set A. So these 2 equivalence relations containing the element 1, 2. And also they may ask what is the smallest equivalence relation from the set A 1 to 3. That is the first one. And what is the equivalence relation containing the element 2, 3? How many number of equivalence relations containing the element 2, 3? That is also 2. What is the number of equivalence relations containing the element 1, 3? That also we can write one. Two equivalence relations. Okay, we can answer. I think so many questions they asked here, and then which is a reflexive, symmetric, and but not transitive. There is another question is there. This is all equivalence relation: reflexive, symmetric, and transitive. Okay. So and then the transitive relation, the first one we call it as a transitive relation. How it is a transitive relation? How can you write it is a transitive relation? Can anyone tell me that first A1, the set A1, it is reflexive. Of course, it is obviously it is reflexive, and is symmetric. Yes, it is symmetric. And how can you say it is transitive? Anyone, madam? Sir, how it is a transitive? Can you how you can describe it is a transitive relation, or how can you define it is a transitive relation?
A, B belongs to the set, and if any element B, C does not belong to the set, then obviously it is a
transitive relation. Okay.
Am I right, sir?
Correct, sir. Correct, sir. Yeah.
Thank you, sir.
A, B. Okay. Actually, there are so many things we can correct only, but we have to write correct, not disproving. Disproving means we have to give example, or authentically we have to say something about the definition. We have to disprove means it is not transitive. If it is not transitive means you can say. So if it is a transitive means okay, A, B belongs to A R1 or A1, and B, C does not belong to that. Yes, sir.
Yes, sir. That's what I said.
So that how can you say that it is a transitive? So just really I was discussing. Yeah. Is there any?
I also had the same doubt, sir.
Yeah, that's what. No, we are going to discuss about that point later. Next topic is that one only. Just I am introducing here itself. I am starting. Okay, let us have that. Let come back to this. Let us come back to this. Is it just I want to know that this is a very important. We are also struggling to find out the correct reason. But what we know that what we experience that we are sharing with you. So just we'll come to the conclusion at the end. Okay. Now about transitive relation. You can have it. About that transitive relation. Now there's the same question what I asked. That is, we are going to see. 1 second. Yes. Now we are going to see that transitive relation differently. This question I'll take. Simple is a textbook question only. A relation R in the set N of natural numbers defined as set of all x comma y such that y is equal to x plus 5 and x is less than 4. X is less than 4 means natural number 1, 2, 3 only. Check whether it is a transitive relation or not. Yeah. So we are going to check whether it is a transitive relation or not. So the relation R, I am writing it in the roster form. Suppose if x is equal to 1, then y is equal to 6. Yeah. And x is equal to 2, y is equal to 7. I'm writing the relation in the roster form. So 3, 8. That's all. There is no other ordered pair here because x is less than 4. The natural numbers less than 4 is 1, 2, 3. So this is a relation what is defined here. So of course, obviously it is not reflexive. It is not symmetric. Okay. If it is not reflexive, we are giving that 1, 1 does not belong to R. So therefore, it is not reflexive. We can give because and at R2, 2 we can write, or you have to give particular example. And the symmetric 1, 6 belongs to R, but 6, 1 does not belong to R. Therefore, it is not symmetric. That's okay. But whether this relation is transitive or not. Yeah. Can anyone say that why is it transitive or not transitive?
May I, sir?
Yes, ma'am.
It is transitive.
Yeah.
Because from 6 there is no relation, or from 7 and 8 the second ordered pair is not there.
Okay. So actually that 1, 6 and 6, 11 should be there. Am I right?
Yeah. Some other relation from 6 should be there. It is not there here, so it is transitive because it is not violating the statement of the transitivity.
Okay.
Sir, can I?
Yes, ma'am.
In general, A comma B belongs to R, but there is no situation to take B comma C belongs to R and hence to prove A comma C belongs to R. So since there is no such a situation, it is considered that it is a transitive relation.
Okay. Welcome, ma'am. Thank you. Any other reason? Anybody else? Good, of course. Any justification? It is a transitive relation, ma'am. Anyone can share, please. Actually, the transitive relation definition is A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. If it is there, for every A comma B comma C belongs to the set A or A comma the ordered pairs belongs to the set of the relation or whatever it is. So this is the transitive word. A comma B belongs to R and B comma C belongs to the relation. If the two ordered pairs belong to the relation, that implies A comma C belongs to R. So this is a definition of a transitive relation, right? Now, if A comma B belongs to R, that is 1, 6 belongs to R. Suppose when can you say it is not transitive? When can you say it is not transitive?
If A comma B belongs to R and B comma C belongs to R implies A comma C does not belong to R.
Very good. Yes, sir. Yes, sir. That's what. So when A comma C does not belong to R, then it is not transitive. Okay, that is very clear. That is the definition of transitivity. A comma B belongs to R and B comma C belongs to R implies A comma B does not belong to R. So if A comma B C does not belong to that relation, then it is not transitive. It is not transitive. That is we are sure. Not transitive. When you say transitive or not transitive, either a relation be transitive or not transitive. Only two possibilities. Okay. Suppose here A comma B belongs to R, but B comma C itself not there. So the reason we can say that, I have read some other book like that, we cannot say it is not transitive. We cannot say it is not transitive, so that it is transitive. Okay, this is justified in that way. Two negation of the statement, two negation statement. So if the two negation makes it is a true statement. That's what we cannot say. This it is not transitive. We cannot say A comma B belongs to R. 1 comma 6 belongs to R, but 6 comma 11, 1 comma 6 belongs to R, but 6 comma 11 itself does not belong to R. That means A comma B is there, but B comma C also not there. So we cannot say it is not transitive. That's what I read somewhere else. That is also I'm sharing it here. We cannot say R is not transitive. Therefore, R is transitive. Understand? We cannot say it is not transitive. Because for not transitive, A comma B must be there and B comma C must be there. Then A comma C is not there, means it is not transitive. But A comma B only is there. So B comma C itself not there. Therefore, we can't say it is not transitive. So two negations here. We cannot say R is not transitive. Therefore, R is a transitive. In this way also we can justify like that. I read some book like that. R is a transitive. Two negation makes a statement is true. That is, we have studied that two negations, negation statement or double negation, and that what you call mathematical reasoning, one chapter in the 11th standard is coming like that. So two negation statement. We cannot say R is not transitive. Therefore, R is transitive. So here in this case, this relation R is a transitive relation. Okay. Now we are going to see one more example for the transitive relation. Yeah, this is also interesting. The students will be very interested to motivate to reason out here. And a relation R in the set A of human beings in a town at a particular time given by X comma Y such that X is a wife of Y. So a set of all human beings in a town at a particular time is given by the relation wife. Is it X is a wife of Y? Is it a transitive relation? Yeah. So X is a wife of Y. It is because X is a wife of Y means Y is a male. So that Y cannot be a wife of any other element or any somebody else. Therefore, Y is a male. So the second element is not possible here. That is very clear. Therefore, it is transitive because we can't say it is not transitive. We cannot say if X comma Y belongs to R and Y comma Z belongs to R means if X comma Z does not belong to R means not transitive. X comma Z belongs to R means it is transitive. But here X comma Y belongs to R, but Y comma Z does not belong to R. Therefore, there is no second option, second element. Therefore, this also we cannot say it is not transitive. So that it is a transitive relation. Yeah, this example is a typical example. X is a wife of Y. Y is a male here. So male, it's therefore that gender. Therefore, it is not possible. Y comma Z is not possible in the relation. Therefore, we cannot say it is not transitive. double negation is coming. Therefore, it is a transitive relation. This A subdivision A is a transitive relation. Same like that previous one. And the second example is x comma y such that x is a father of y. Is it transitive?
Yes, sir.
Is it transitive, sir? Yes, sir.
Yes, sir, it is transitive by using the double negation.
How, sir?
X is the father of y.
Okay.
Means X is the grandfather.
Yeah.
Y is the son.
Okay.
Father.
Very good. Okay.
Y comma
Z. So
Z.
Y is a father of Z. So
grandson only will come.
Okay. Very good. In that case, it is transitive. Suppose if any other case comes, if Y is a female.
I think so, like option A. So the here also using double negation, it will be transitive. I assume so, sir.
Correct, sir. Correct. Suppose X is a father of Y. If Y is a male, then Y can be a father of Z. Suppose Y is a female. What can
Even in case of male, it will not be transitive because the relation between X and Z will be what? X is the grandfather of Z, right?
Yeah. That case, it is not transitive.
Not transitive. In both the cases, male or female, it will be not transitive only.
No. The female means it is transitive only, madam. If Y is a if Y is a female,
yes.
Then X is a father of Y. So Y may be a daughter.
Y does extend. Okay,
Y cannot be a father. Yeah. So the second element is not possible. Yeah. So in that case, it is a transitive.
So
but we have to say it is not transitive because.
No, I'm not coming to the conclusion. I'm not coming to the conclusion. So there are different cases are there. X is a father of Y. And Y, if it is a male, Y can be a father of Z, but X is a grandfather, so it is not transitive. Here it is very clear that it is not transitive. Am I right, sir? Venkateshwar, sir?
Yes, sir, correct.
So in that, your case is not transitive. The second case, if Y is a female, suppose if Y is a female, X can be a father of Y, but Y cannot be a father, so that it is transitive. Because here only the double negation comes. That is X comma Y belongs to R, but Y comma Z does not belong to R. So we cannot say it is not transitive, therefore it is transitive. So some cases, if Y is a female, it is transitive, and Y is a male, it is not transitive. So at the whole, this relation is not transitive. Am I right, sir? Yes, ma'am.
Y is a female, so not transitive. That no need to tell, sir. That's let us not tell that. And it is, see, when you are considering Y as male, it's not transitive.
Not
and
transitive.
If one case is not transitive, that's all. That's it.
Yeah, that's what I wanted to say.
Yeah.
If one case it is, that's
no
what
need,
I wanted.
No need to discuss in pieces, sir. Now.
Yes. So why one case it is not transitive means it is not transitive. Yeah, very clear. Yes, ma'am.
And when we are not able to say it is not transitive, when we are not able to say assertively it is not transitive, we assume that to be transitive. That's
transitive. Yeah, that's what. Yeah, welcome. Thank you. Is it clear, sir? Now? Yeah.
Yes, sir, clear now, sir.
Yes. And some more examples I have given. That's what. Let R be the relation on R defined by A comma B such that modulus of A is less than or equal to B is a relation. So that R is neither reflexive nor symmetric, but it is a transitive relation. Yeah. Neither reflexive nor symmetric, but it is transitive. A simple example only, we can show that it is neither reflexive. Some typical example we have to give. Anyone can say that it is not reflexive? Anything can tell me? Not symmetric, not reflexive, but it is transitive. Transitive, of course, it is clear. Any a real number modulus of is less than or equal to b, and also b is less than or equal to c means a must be less than or equal to c. Is the modulus of a means it is a positive number. Whatever it is, positive real number or 0 is less than or equal to b means b should be a positive number. Then only it is this relation is true. This ordered pair.
And none of the number cannot be less than the same number.
Yes. Therefore, it is a transitive relation. Yeah. So not reflexive. Not reflexive. Am I right, sir? Because this -1, -1 does not belong to R. -1, -1 does not belong to R. Because R is a real number, set of all real numbers it is defined. So -1, -1. So modulus of absolute value of -1 is 1. So 1 is not less than or equal to -1. Therefore, it is not reflexive. Right?
Yes,
sir. Like that, a symmetric, we can give any numerous example. 1 less than or equal to 1, 2 belongs to R, but 2, 1 does not belong to R. Anything we can give obvious example. Therefore, it is a reflexive and a symmetric. Not neither reflexive nor symmetric, but it is a transitive. Also, in this case, these are all some examples we have to. Yeah. R be the relation on the set of rational numbers Q defined by R is equal to set of all x, y such that 1 plus xy greater than 0. Show that R is reflexive and symmetric, but not transitive. Do you agree, sir? Or anyone?
Yes, sir, it is reflexive. Yes. The product of two negative numbers is positive.
Yeah.
So definitely it will be 0, greater than 0 only.
Yeah. Negative two negative because x and y, x, x. Yeah, yes, sir. Yeah. So x, x belongs to R. So for every x belongs to that relation. For every x, x, means 1 plus, that is, this implies 1 plus x into x, 1 plus x squared is greater than 0. For any real number x squared is a positive number. Therefore, 1 plus x squared is greater than always greater than 0. So, therefore, it is a reflexive relation. Am I right, sir?
Yes, sir, correct.
Yeah. And then, what about a symmetric? So 1 plus xy.
The product is commutative, so we can say.
Yeah, that's what product is commutative. We can say like that 1 x, y belongs to R, implies 1 plus xy is greater than 0. This implies 1 plus yx greater than 0. Therefore, y, x belongs to R. Yeah. Therefore, for every x, y belongs to that list. Therefore, it is symmetric, but not transitive. How can you say it is not transitive? We have to give a particular example.
Maybe fractions we can take.
Madam, Lasita ma'am, hello.
Yes, sir.
Are they ready, madam? Are you this?
Yeah, you have to make me host, ma'am. So, of
okay.
course, sir.
Yes, yes. So
Then
we'll
we can
after
share.
finishing this, we will come back.
Yeah.
That is GeoGebra. Nice one. Can you give example of this minus 1 comma 0 minus 1 comma 0 belongs to R because 1 plus 0 is greater than 0. Okay. And the 0 comma 2 is also belongs to R, but minus 1 comma 2, am I right? Minus 1 into 2 minus 2. 1 minus 2. Yes. Minus 1 comma 2 does not belong to R. Therefore, it is not transitive. You have to give a particular example. We have to give one particular example so that it is not transitive from the set of real numbers. So minus 1 comma 0 belongs to R, implies 1 plus minus 1 to 0, 0. 1 plus 0 greater than 0. Of course, it is true. And 0 comma 2, 1 plus 0 into 2, 1 plus 0 is greater than 0. But minus 1 comma 2, 1 plus minus 1 into 2 is minus 2. 1 minus 2 is minus 1, which is less than 0, not greater than 0. Therefore, it does not belong to the relation. Therefore, it is not transitive. So, reflexive, symmetric, but not transitive. Yeah. So, I think we have discussed the transitive relations and the equivalence classes. One more example in the textbook, A less than or equal to B squared. Check whether the set of all or equal to set of all x comma a comma b such that a is less than or equal to b squared, and a and b from set of all integers or real numbers. We'll take real numbers. Is check whether it is a reflexive relation or symmetric relation or a transitive relation. Now, madam will give.
For that question, I would like to give a visual proof for that using GeoGebra.
Yes.
So usually we give examples to disprove that reflexivity and symmetry and all. Sir, if have you made me host, sir?
Yes, ma'am. Yes, ma'am. I'll stop sharing. Any other doubt in the regarding this? We can share here. Otherwise, we'll go to next topic. Anyhow.
So I'm sharing my screen.
Yes, ma'am.
This question.
Oh, you can share. Okay.
Sorry, I will make it a cube. Sorry, square. Any question we can do that. Let us, since you already said that.
Yes.
This one square itself we will take. One
okay.
second,
A less
sir.
than or equal to B squared. Yes,
yeah, 1 second, sir. So here I'm taking square itself, a lesser than or equal to b square. In terms of the coordinate system I am taking. So if it is x comma y, it is nothing but x lesser than or equal to y square. So if you are taking x is equal to y square, it is a open rightward parabola, right? Open rightward parabola it is. So this is the proof using GeoGebra. Once are you seeing my screen? 1 second.
Yes, ma'am. We can able to see your screen.
Yes. So that inequality idea in class 11 children would have learned which side to be shaded and all using the ax plus by plus c less than or equal to 0 greater than or equal to 0. With that they can identify which region to be shaded. So if they shade the region of x lesser than or equal to y square, they will be able to understand that this is the region. This is a shaded region is the region which defines that a capital R. So all those points in the shaded region are part of the capital R, belongs to the relation R. Now, how can we prove this is reflexive or not reflexive? 1 second, I'm not able to, yes. So here, if I draw the line x is equal to y, you see the region, the points from 0 to 1, that line lies outside the shaded region. The meaning is that decimal numbers, for example, 1/2, if you are taking 1 by 2 comma 1 by 2 doesn't belong to capital R, because 1 by 2 is not lesser than or equal to 1 by 8. So these points, right, these points, if you substitute, it will not be on the line y is equal to x. If at all that y equal to x line completely lies on the shaded region, we can say that it is reflexive, isn't it? Because an element A is related to A itself, or x is related to x itself. So that those points will actually lie on the line y is equal to x. So this is one method to show that it is not reflexive. So if you give the visual idea, they will know that these are the points to be substituted in that and prove that it is not reflexive. That idea they will get. Now, in order to prove the symmetry, we can take any point on the shaded region. Here I have taken 2, 5, and I will reflect it on this line. So here I'm taking the reflector about a line. So I'm clicking the A and this line. So that point, you see, A dash is the reflection of the point, the capital A. It lies outside the shaded region. That means 2, 5 belongs to capital R, but the reflection 5, 2 doesn't belong to capital R. In that way, we can say that it is not symmetric. Maybe there are other points which you take the reflection, it may lie on this in the shaded region itself. But with that, we cannot do the conclusion. If I take the point E here, okay, and if I reflect it about this line, that will lie on this E dash will lie on the shaded region itself. But we cannot say that it is symmetry because we are getting violations to disprove that case. Similarly, how to show that it is
Madam, one doubt.
Yeah.
The transitive only that 0 to 1, only the 0 to 1 it is sorry, reflexive, sorry. 0 to 1
the decimal points if you
decimal
substitute
point
it will
not
not
to,
satisfy. Yes.
Okay, 1 by 2.
1 by 2, 1 by 4, those kind of points, that is between 0, 1. See, that line lies outside the shaded
not
region.
lie on the
Yes. Yes.
The shaded region.
Yes. If at all it was reflexive, this line would have completely lie on the shaded region.
Okay.
And in order to prove the transitive case, here let me take a points.
So symmetric only that way some many points lie on the region.
Yeah,
but,
any point you can take here. Select a point here.
Okay.
Select a point here. Try to reflect it about the line. Take a point F here. Try to reflect it about the line. So in order to reflect it, click on the point and the line. Then this point F dash lies on this itself. So we cannot say that. Let me take another point. So maybe somewhere here.
Okay.
Somewhere far off.
Yeah,
if
1, 2. Okay.
Yeah, if I take it. Here the G dash lies outside. Okay. So that point can be an example for proving not symmetric.
Not symmetric.
Yes. And in order to prove the transitivity, what we have to do is we will take points like here I have taken already 6, 3 I have taken a point. Okay. And 2 points I have taken which lies on the shaded region. So okay.
3, 2 and
3, 2 and 6, 2. So my first point is 6, 2. Okay. My second point is sorry. The relation should be from where to where? 6 to 3. Yeah, it should have been 2, 3, I think, right? 6 to 2, the resistor relation.
No, correct, madam. 6, 3 and 3, 2. 6, 3 belongs to R and 3, 2 belongs to R.
Belongs to R. 6, 2 doesn't belong. That is, you can actually show this here by drawing a right triangle connecting the CD. These three, if you join, you will get a right triangle, and one of the vertex of the right triangle, if it lies outside the shaded region, we can say that it is not transitive. So 2 of the vertex B dash and C lies here inside the shaded region, whereas D lies outside the shaded region.
Okay.
So in that way, we can prove it is not transitive.
So any other example also you can. Yeah.
Any other example, any real valued functions we take, we can try this method.
Lasita, you do for one equivalence relation.
Equals.
One equivalence relation, one example. I will take first, ma'am. 1 second. You proved, no, sir. One example, which was that?
Yes, ma'am.
Our previous question was modulus x lesser than y it was. So this was the shaded region for that.
Okay.
This was the shaded region. If we draw the y equal to x line, also you see here negative points. If you take, it will not lie on the line y equal to x.
Yeah.
So it is not reflexive.
X minus y is an integer.
What is the R to R, sir? I mean, is it only? No. Defined on which set is matter, sir?
Relation R in the set of Z of all integers, man.
Set of all real numbers they are asking, sir.
Sir, I want set of all real numbers, sir. We can prove only for that cases. So here also the earlier question it was. It is not reflexive here. Yeah. In that way, we have to take a points where it doesn't lie here. If I take one point out inside here, for example, if I take a point here and I reflex it about the line y is equal to x, a dash lies outside. So when you are reflexing, what happening is x and y are interchanging its positions. So x comma y belongs here, but y comma x doesn't belong. That idea we can prove here.
Okay. But A less than or equal to B cube also it is not.
Ma'am, I will find out one example, ma'am, for equivalence relation in the next class.
In textbook, we don't have.
We don't have in the textbook, yeah.
Yeah.
Real number system, we don't have an example.
Yes, yes.
But the A less than or equal to B cube, ma'am. That also.
A less than or equal to?
Graph of B cube.
Yeah, we can do that. One second.
Y cube.
This is the y cube graph. X less than or equal to y cube graph.
Okay.
So this is the shaded region which lies. Here are the points from 0 to 1 as well as these negative numbers.
Negative numbers.
Will not prove the reflexive case.
Okay.
And similarly, symmetry and transitivity. Transitivity, in order to take, we have to prove all three vertices of the right triangle should belong to the region itself. If not, we have to say it is not.
Okay. -1 only belongs to there.
Yeah.
And after that, okay.
So this will give an idea which point to be taken in order to disprove the cases.
Okay. So 0 to 1, if we take madam, okay. 0 to 1 reflexive, we have to take the 0 to 1.
Yeah.
And also
these points, sir, these points
-2,
from 0
-2.
to 1 as well as these points -2, -2.
Yeah, like that. More than -1.
More than yeah, lesser than -2.
Sorry, lesser than.
These points to be taken.
Yeah. So -2, -2 means does not belong to R.
Does not belong.
So -2 less than or equal to A -8 is not true.
Yes.
Okay. Therefore, it is not reflexive.
Not reflexive.
Yeah. And 1/2, 1/2 does not belong to R.
Yes.
Yes. Therefore, it is not reflexive.
Yes.
Okay. And the symmetric.
Symmetric point
we have
to
to
reflex.
Point and reflex.
Yes, sir. Sorry. 1 second. Sorry, I think I missed my graph. 1 second.
Yeah, please.
It's okay, ma'am. We have understood.
Yes, sir. In my next class, I will show in detail, sir.
Sure, ma'am.
Yeah.
This is neither reflexive or symmetric.
Not symmetric and yeah, not transitive.
Not transitive.
Yeah. Shall I stop share here?
So in all inequalities, when the question involves inequalities,
Yes.
shading will come.
Yes.
Yeah.
And
Yes.
when it is not inequality, it will be just a curve or a line.
Yes.
So if I give the question as y is equal to x, on a set, real number set, the relation is y is equal to x. Y is equal to f of x is equal to x.
Yes.
If that is a function, only that line will be there.
Yes.
Yes, yes,
Only one line. And if it is y is equal to x square, only that parabola will be there.
yes.
Yes.
That time, how to tell them
Yeah.
that?
Yes.
So y is equal to x is the relation now.
This is y equal to x.
Yeah.
Yeah.
Only a single straight line will
Yeah.
be the
Only a
relation.
single.
Yeah.
Yeah.
In this
So-
case, it is reflexive because each and
Reflexive.
every point is
Yeah.
on
Up
that
and down.
line itself.
Yeah.
And we don't have any a comma b exist in that one, so it is not violating the statement of symmetry.
Exactly. That's
So
why we say
it is symmetric as
It
well
is
as it
symmetric.
is transitive.
transitive.
Yes, ma'am.
Yeah.
And
Y is equal to
the groups will be like equivalence classes. It will be divided into infinite equivalence classes.
Yes.
Yes, ma'am. Yes, ma'am.
Infinite equivalence classes.
Yes,
If
ma'am.
it is
Each single number is a equivalence class.
Yes, ma'am.
each single number is an equivalence class.
Equivalence
Yeah.
class. Yes.
So infinite equivalent classes we can
Yes.
have.
Yes.
Yeah.
And y is equal to x square.
Y is equal to x.
Yeah, there also we don't have a shaded region, no, ma'am.
No
So,
shaded region. That's
no
why I'm
shaded.
saying.
I mean,
But it
will
cannot be reflexive.
y equal to x square. 1 second. This is y equal to x square.
Okay.
So the line y equal to x here,
Yeah.
but it's an equation, right? Y equal to x square.
So when it is not shaded, on the line, the points which lie, only they will satisfy reflexivity.
Yes.
Yes.
Yes, ma'am.
All
Yes.
other
Yes,
points will negate.
Negate. Yes.
Yeah.
Only
So
1 comma 1, 0 comma
yeah, 1
0.
comma 1 and 0,
And 0 comma 0. Yeah.
only will satisfy reflexivity.
Only
Only
satisfy.
those
all-
elements are there in
Yeah.
that are actually.
Because they are intersecting with the line.
Yes. Yes. Intersection
All
only are
other
there.
points they do not satisfy, so it's not reflexive.
Not.
Yeah. Yes.
And this
Great.
one, yeah.
y equal to x cube.
Y equal to x cube.
Same way.
Yeah, that already we saw
curve.
that. Yeah, 1 second.
But we included lesser than
That is
equal to.
Yeah, lesser than or equal to, yes. Y equal to x cube graph.
Only 3 points of intersection will come.
Y equal to x cube graph.
Yeah.
This is y equal to
Yes.
x cube graph.
So
This
3
is y equal
points.
to 3 points.
Only it
0,
will
0,
satisfy.
0, 1, 1, minus 1 belong to capital R.
Yes, ma'am.
So yeah, it is only the 3 points.
Yes.
X comma x. Yeah, 1 comma 1, 0 comma 0.
0 comma
Yeah.
0.
Minus 1
So
comma
based
minus.
on that,
Only
it
3
is
points.
reflexive. Yes.
Yeah.
And we have to
Other-
show that any other point chosen, now it's reflection. That point will not lie on the curve. So it's not reflective.
Yes.
Reflexive.
Yeah.
Sorry,
If
it is
I
not
choose a
symmetric.
point,
Symmetric.
yes,
Symmetric.
Yeah.
Yeah.
If I choose a point,
Ah,
that a point is not on the curve here, y equal to
Curve.
x cube,
Yeah.
isn't it?
yeah.
In that way only, no, ma'am.
No. On the curve, I have to take a point.
On the
On the curve.
Yeah.
And that is what is a number?
One
What is the location? Something.
sorry, I will take a point. I am not able to take a exact point here. This is 1 comma 1.52,
Yeah.
3.98.
Yeah.
2 comma 8.
Its reflection, its symmetricity should be reflection in y is equal to x line.
But that
That will not be there on the curve. On
Yeah.
the curve.
On
So
the
it's
curve.
not. So it's not symmetric.
Yeah.
not symmetric. Yeah.